I would like to show my gratitude to organizers of DCASE workshop. My name is Shinichi Satoh, National Institute of Informatics, Japan. Today, I would like to talk about visual recognition research and its relationship to benchmark dataset. First, I'd like to confess, my background is visual recognition, especially image and video semantic retrieval, semantic analysis, mining, and so on. And I understand that DCASE community focuses on acoustic signal analysis. Then why visual recognition? Maybe many of you may seen this kind of chart. Actually, this shows the performance of one type of visual recognition. And this shows the performance. Actually, this corresponds to classification error. Lower the better. And this corresponds to the years. And as you can see, as the time going on, the performance is getting better and better. And in 2010 and 11, performance is rather not so good, while in 2012, the error rate was significantly decreased. And this performance is done by Professor Jeffrey Hinton, Turing Award winner, by his introduction of a deep learning technique to visual recognition. And afterwards, people started to use deep learning technique to further improve the performance. And currently, visual recognition performance surpassed human performance. So deep learning technologies made breakthrough in visual recognition. And actually this task was image classification. And ImageNet was used for benchmark data. I guess many of you have seen this kind of chart, but many of you don't know what exactly ImageNet is, which was used to evaluate this performance as a benchmark data, and what kind of images are in the ImageNet dataset. I'd like to visit that kind of topics. In addition, I'd like to explain about the evaluation of visual recognition tasks along with benchmark dataset. And a couple of issues found will also be visited. Okay, let's move on. I'd like to explain about typical pipeline of visual recognition, and image classification will be taken as an example. This is image recognition classifier, and this will be given unknown image like this or this. And then classifier will output a lion for this image and penguin for this image. And to evaluate the performance as well as to train this classifier, benchmark data is used. Benchmark dataset can be like this, and it is composed of a couple of target class categories like dog or street sign, and couple of example images belonging to each of these categories. Like for dog, those images are given as a example of dog category images, and those for street sign images. So benchmark dataset is used to train this classifier as well as evaluation. And that should cover large variation to ensure good classification performance in training as well as reliable evaluation. And normally end-to-end training is used. End-to-end means classifier will be given input, image, and output only. And after the training, people don't care what's going on in the classifiers. All right. Um, I would like to explain about a couple of different kinds of visual recognition. So this corresponds to image classification. Maybe unknown image will be given to the classifier, and expected output could be like this. For instance, since this image contains person, sheep, and dog, possible output as a class categories can be person, sheep, or dog. Other type would be object detection. Given this image, not only the name of categories, but also the location of each object will be output, like a person would be here, and sheep, sheep, sheep there, and dog. Others would be object segmentation, not only this kind of rough localization as a rectangle bounding box region, but also pixel-wise classification result is expected to be output. And further example can be instance segmentation, where each individual sheep will be identified. And also, there are other kind of visual recognition tasks like image captioning, visual question answering, scene graph representation, and so on and so forth. Uh, some of them will be visited in the following presentation. Okay, so first, let me explain about image classification. And this shows the very early data set for image classification. This is called COIL 100. This appeared in 1990s. So this dataset contains 100 objects, and the goal is to identify object by given unknown image despite the view angle differences. So these example images, and um, each row corresponds to each type of object. So you can see each individual object are taken by from different angles like these. Um, so this is one example of image. As you can see, there is no background, rather just black background. So in that sense, it's easier. And there is no intra-class variance because this dataset contains uh, one individual object as one class, like these as one class, these as one class, and so on and so forth. So no class variance in there. So in that sense, so this dataset is rather easy. However, so this benchmark data for sure improve the performance of visual recognition. So based on that, more complicated data sets were proposed. This is example, Caltech 101 and Caltech 256. Those were appeared in 2000. Each of them contains 101 and 256 object categories. Here, this dataset contains deals with the categories rather than each independent object. So this is one example, chair category. So this contains many different kind of chairs in there. Plus, as you can see, these images contain complicated background. So to deal with this dataset, the method need to handle intra-class variation as well as background clutter. I'd like to explain how this dataset is composed. First, images were obtained by a web image search by giving object category name as a query. And of course, web image search engine may generate a couple of course, correct search result as well as wrong result as well. And then irrelevant images were manually eliminated. So this is some tedious task, but they did that. So this is good, and this further improve the performance of technology of visual recognition. However, those datasets has some problem. So they have rather arbitrarily chosen categories are used. For instance, even though only a few hundred categories are selected out of all from the universe, and they contain airplane, camera, chair, and so on, such kind of more common categories, while they contains trilobites or bonsai as categories. So it's rather difficult to say that whether those kind of categories can be included only in a few hundred categories in the universe. So there is some bias in the selection of categories. Then yet another data set it was then proposed. This is very famous one. Now it's intensively used, which is ImageNet, which first appeared around 2010. In ImageNet, object categories are rather systematically selected. They refer to WordNet. This is concept dictionary, and they basically select all noun phrases termed synonym or synonym set or synset. They were systematically selected as categories. In total, 20,000 categories were selected. So there is no arbitrariness. In the sense, it's good. And candidate image were again collected by a web image search. Of course, they may contain some noise, error, and they are manually cleaned. However, it's a bit too much to do that in, for instance, only by university laboratory members, and they use the crowdsourcing. In particular, they use Amazon Mechanical Turk to clean the dataset. And in total, it's still evolving, but currently it has 14 million images, and in the sense, it's very large dataset. How it looks like. So that is composed of a couple of category names like fox, English setter, Scotch terrier, street sign, kayak, and so on, so forth, and example images of each categories. And of course, this is used for image categorization, image classification, and then objective would be to classify given unknown image into right category. For instance, in this case, Blenheim Spaniel could be right answer. Now, based on ImageNet, yet another data set is composed for specifically for benchmark. It's called ILSVRC. This stands for ImageNet Large Scale Visual Recognition Competition. So this is designed especially for competition, and this competition ran from 2010 to 2017. And actually, this is trimmed version of ImageNet. It contains 1,000 categories and 1.2 million training data, 50,000 validation data, and 100,000 test data. And as you can see, this is yet another dataset, Pascal, which is more or less similar to Caltech. And those kind of initial dataset contains rather rough categories like bird, cat, or dog. But in ImageNet and ISVRC, it contains more fine-grained classes. Like for bird, they contain flamingo, cook, and so on and so forth. And in cats, it contains Egyptian cat, Persian cat, and so on and so forth. And dog as well, Dalmatian, and so on and so forth. So this is more fine-grained because 1,000 categories is rather very large. And so again, this chart, so this was evaluated using ILSVRC dataset. So as I mentioned, so deep learning technology made a breakthrough, and currently error rate is, well, in 2012 it was 16%, but now it's 3%, and now less than 3% has already been achieved. And it is said that human error rate is around 5%. But I have to mention that this human error rate is very hard to achieve. Uh, I would say I cannot do this. One is because it's still very fine-grained, 1,000 categories. And actually, this trimmed version, ILSVRC, contains 90 different dog breeds as classes. Well, I would say I cannot differentiate given one unknown image into 90 different dog breeds. It's for me, it's impossible. In addition, ImageNet original version contains 120 different dog breeds. It's amazing. Okay, so let me explain about the other visual recognition task. So one is object detection. As I mentioned, so in addition to not only to tell what kind of object in given unknown image, but also in object detection, the system is expected to locate the region of object. For instance, in this image, this region should be detected as train, and this as car, this as car. And for this image, this should be chair, this should be dining table, and this can be bottle, and so on and so forth. And one of very famous object detection benchmark data is Pascal POC. This contains 20 categories. Next example is object segmentation, which is more complicated version of object detection, not only bounding box, but also pixel-wise object categorization is expected as a output, like here maybe person, here sofa, laptop, and so on, bus, car, bicycle, horse, and so on and so forth. And a very famous data set is common object in context, or it's called the Microsoft Cocoa dataset, and this contains 80 categories and 300,000 images and 1.5 million segments annotated, and it's used for benchmark and training. Let me explain about more complicated task, which is first one, image captioning. So goal of the task is to give the description of given image. Like for instance, this image will be given to the system, and expected output can be the explanation. In this specific example, expected output can be man in black shirt is playing guitar. And maybe other example, so given this image, expected output can be black and white dog jumps over bar. So this is rather complicated. And training data, benchmark data for image captioning is, I would say, more complicated. So one is because captioning, explanation of given one image may not be unique, can be in multiple variation. And if we ask people to give caption for given image, that may vary from person to person. For instance, so actually famous data set is Microsoft Cocoa, and this is taken from that data set. So this is image. And actually in MS Coco, each image will be given multiple possible captions as ground truth data. Typically 5 captions will be connected to each image. And for this image, the first one is, say, boy on motorbike with small white dog in front basket. So maybe you can notice there is some white thing in the basket. And if you take a closer look at this, actually this is white dog. So this annotator understand that this is white dog. But if we take a look at maybe this one, a man sitting on a scooter with a little basket in front of it. So no description about white dog. So maybe this annotator cannot find that this is dog. So the caption may vary, and so it's very hard to define the ground truth. So in the sense, so evaluation is rather complicated. Of course, basically the evaluation will check if generated caption well matches with the human generated captions like these. And in doing that, they use multiple metrics like a blue, meteor, rouge, cider. And actually these metrics are designed for machine translation. I won't go into detail, but those kind of ground truths as well as evaluation is rather complicated for image captioning. Other task is a visual question and answer or visual question answering. What is this task? So this task is like images will be given, like this image is given, and this question is also given. So this is text form, and in this specific example, question is the TV on? And for this image, as you can see in this set, TV set is on, so expected answer would be yes. And for this image, so TV is off, then expected answer would be no. So this is yes and no question. So it's rather more somehow intelligent visual task. While this is a bit maybe easier, while there can be some other more complicated question like what sign is this? What question? And for this image, answer can be handicap. For this, answer can be one way. And other more complicated one can be maybe this. How many donuts have sprinklets? Sprinkles, I'm sorry. And so for those images, so I don't know the right answer, but according to the ground truth, right answer for this image would be 3, and right answer for this would be 2. Ground truth as well as the version for visual question answering is more complicated, while I will touch on this topic in later slide. So let's come back to this topic later. Okay, yet another visual task would be visual genome, or it's scene graph representation. This can be final output, and it's like object detection, like given this image. The expected output can be composed of a couple of bounding box for each object, like this corresponds to this person, this corresponds to this lady, and this corresponds to this object. While in visual genome as well as scene graph, this contains not only detected object region, but also object relationship among objects is also given. Like in this example, this man jumping over fire hydrant, and this woman is standing behind the man, something like that. It's more complicated. And actually, it's very difficult to give this kind of ground truth data. And to do that, they use 33,000 workers. Actually, they use crowdsourcing as well, and they use a crowd worker, and they use this kind of pipeline. First, they ask one crowd worker to draw 3 bounding boxes and 3 descriptions per bounding box. Then another worker add more descriptions different from previous ones. And these 2 steps are repeated. And finally, at least 50 bounding boxes will be collected per image. And then other workers decompose them into objects. So this level bounding box can be like this. Like this one corresponds to man is jumping over hydrant, something like that. And then this worker may decompose this into each different objects. And then further other workers add attributes, relationships, graphs, and so on and so forth. And repeat it. And finally, the result will be verified by the other workers. So it's very complicated. But anyway, this representation is very useful for further semantic analysis of images. Okay, now I would like to visit some issues exist in those kind of benchmark data. To do that, I'd like to visit yet another benchmark data, which is TrekFit. So actually, TrekFit is a conference series aiming at benchmarking video retrieval. So they deal with video. It started from 2003 and it's running till now. And they impose a couple of different tasks from time to time. And one of them is high-level feature extraction. The goal is to classify given video shot into semantic categories. So it's more like image categorization, image classification. While there is key difference between this TrekFit dataset and other image benchmark dataset like Caltech and ImageNet. Namely, for TrekFit, they first collect video. For instance, in some cases, they use news video program, and they obtain those kind of videos from broadcast station. And as a situation, variety of TV programs are collected from national broadcast archive and so on and so forth. So they collect data first, they fix data first, then set some tasks like define classes, categories. So it's totally different. The other image level benchmark data like Caltech or ImageNet, they define categories first, then collect data according to category. So that may cause some, I would say, skewness. This graph shows the distribution. So these corresponds to class categories, and this corresponds to the number of samples in benchmark data. And this corresponds to TrekFit, and this corresponds to ImageNet. So if that distribution is natural, then the distribution, it is known that the distribution may follow power law, namely JIP law, which is inverse of the rank. And this line corresponds to inverse of the rank. And as you can see, TrekFit roughly follow the power law, while ImageNet is totally different. Well, this is a natural because ImageNet first define categories, and then for each category, they search for images via web image search, and then clean the data set. So in that sense, so it's natural that they have this kind of trimmed distribution. So okay, so this is however, so this is natural. While if we train our classifier based on this unnatural distribution, and if we apply that classifier to natural data, So it's questionable whether the performance is fine or not. Okay, then I'd like to visit yet another benchmark data. And here, task is landmark retrieval. And actually, landmark retrieval is very well studied because of a couple of reasons. One reason is because the definition of the ground truth is very clear. So the goal of landmark retrieval will be that given one image showing some landmark shown in there, goal is to retrieve as many images as possible which contains the same landmark in there. So in that sense, correct answer may correspond to the images having the same landmark appear in images. So in that sense, definition of ground truth is very clear. And there are two very well-known datasets. One is Oxford Landmark Dataset. This contains 5,000 images, and Paris Landmark Dataset contains 6,000 images. Well, those are relatively small dataset, but those are very famous, and both appeared in CVPR. Oxford dataset appeared CVPR 2007, and now it has 3,000 references. And for Paris, appeared in CVPR 2008, has 1.5 thousand references. And because of the well-defined nature of ground truth, maybe many important image retrieval techniques have been studied based on this dataset. I won't go into detail, but they contains a query expansion, database side augmentation, geometric verification, diffusion, and so on and so forth. And so far, very high performance has been already reported based on those datasets, over 90% mean average precision, almost perfect. So people wondered whether a landmark retrieval problem has been solved or not. Answer is no. And one paper pointed out the noise issue in existing data, especially Oxford and Paris. And the error in Oxford and Paris dataset was somehow corrected. And in addition, new, larger distractors were added. Distractors are composed of many images which has no relationship to the landmark classes included in those datasets. So those are basically not related images. So they should not appear in retrieved result. And they also differentiate dataset into easy case, medium case, and hard cases. And as you can see, so those method, this is rather old, and this is state-of-the-art method. And if we use original Oxford data, performance is 90% mean average precision. Paris, 95% mean average precision, almost perfect. However, when they evaluate the performance of this method using corrected data, even for easy cases, performance is like this, or it's rather high, but in hard cases, performance drops to 40% mean average precision in refined Oxford and 98% in refined Paris dataset. So there are still many difficult cases remain. And in addition, since they contain new disruptors, so this can be something interesting. So those are queries, and these images were retrieved by using some retrieval method. And maybe we cannot tell whether those are wrong or not, but actually those are wrong result. And it's very hard to tell by computer. And this as well, this is query and those are retrieved one, but actually they are irrelevant, very hard to tell. There is some lessons. So dataset may contain some noise, and so even landmark retrieval, there are still many issues to be solved. Now, I'd like to explain about the new landmark retrieval dataset, Google Landmark version 2. This appeared CVPR this year. This is somehow considered as a ImageNet of landmark retrieval. This is very large dataset, 5 million images included, and 200,000 instance levels, means 200,000 different landmarks included. And it has this kind of distribution. So some class may have huge number of images in the dataset, like Eiffel Tower or Opera House. Those are very famous, and several thousands images included. However, there are some less known landmark also included. And for instance, this one has only 3 images, I think, included in the dataset. So in the sense, so this dataset has very long-tailed distribution, and I would say this is more real. So this issue should be handled. There is yet another issue in this dataset, that is noise issue. So even though if we refer to ground truth label, for instance, this is one category, and this category images may contain those which may correspond to the same landmark, while this dataset contains those kind of images, and maybe those are wrong ones. And in that sense, dataset has noise in there. And this is yet another example. Those are fine maybe, but those could be noise. So this is how to say, somehow inevitable issue. If you make the dataset quite large scale, then noise can be inevitable. Okay, let's move on to the other issue, visual question answering. So let's check about the ground truth. This is somehow similar to image captioning. So for instance, this is image and this is query. How many of the men are wearing glasses? And actually, the couple of annotators will give the answer to this question, and answer can be 2 5 times, and 3 4 times, and 1 time. So there are variations, and it's hard to tell how to judge based on this ground truth. And for this, what color is the hat? 9 red and 1 orange. Well, it's somehow possible. Now, of course, there are some obvious case. How many birds? And 2 10 times. So no variation. So this is okay, but there are many variations in ground truth data. That is one issue. The other issue, somehow answers biased. In this case, some method referring only to image is used. So can you say question will not be observed, only image, and infer the estimate the answer without a query. However, the performance is rather okay. Overall performance 24%, and for yes no quiz only, it's more than 64%. It's quite high. And amazingly, if we refer only to query without visiting image, performance is rather high, higher than image only. So, in some sense, the data set is somehow skewed. It's quite surprising. Of course, there are many other more complicated questions exist in dataset, but this is this can be observed. Okay, other issue. We will visit the other task, which is video moment retrieval. What is this? So we will be given untrimmed video like a movie and a query like a man is seen speaking to the camera and holding up a paper. And task is to localize the segment, video segment from given untrimmed video, which corresponds to this description. And this specific example, this can be the right answer. So expected output would be the start time of the segment as well as duration, two values. There are two data sets were studied, charade STA and ActivityNet captions. And actually, the start time and duration may have some distribution. And if we plot that, so this corresponds to start time, relative start time 0 to 1, and relative duration 0 to 1. By definition, and each point corresponds to each duration. And the ground truth duration may have some distribution in this space. And by definition, those points may appear only in latter half of this triangle. And for this data set, overall distribution can be this, somehow skewed. There may be one possible answer can be randomly chosen according to this prior distribution. And amazingly, if we refer to any specific word appear in query like open, then distribution can be different and leave distribution can be different. And this data set distribution is rather skewed. This is overall. And amazingly, if a query contains continue, then distribution will strongly skewed in this area only. So this is something interesting. And they check couple of method and so those state-of-the-art method, this is top performer, and they include couple of methods like this. They don't refer to the video at all, but only to query, and of course refer to the prior distribution. And prior distribution only means only this can achieve this performance. It's rather good. And some other more complicated method to analyze query that achieve this rather good performance. And this dataset or blind method without referring to video achieve this quite good performance. So in this sense, so we have to be careful about the skewness of the task itself. Okay, let's visit to the ImageNet again. So ImageNet Grantus may also have some problem. So this chart is interesting. So this corresponds to some of state-of-the-art method in each year, and they generate estimated classes for each image, as well as they show the ground truth level for each image and ask people which you prefer, ImageNet ground truth or predicted level. And for older method, well, people tend to prefer ground truth level. However, for more recent method, people started to prefer estimated result, which is somehow surprising. And they check the error in ImageNet ground truth, and actually there are some problem. For instance, for this image, ground truth image level is peer, By the way, ImageNet allows only one class category per image, so only one peer. However, they may contain multiple objects. So they proposed a new ground truth label for part of ImageNet, which is called real. And in real ground truth, for this image, it contains multiple classes like dock, pier, speedboard, sandbar, seashore. And this is yet another example. Original ImageNet has hammer only, or there are many others, and real screwdriver, hammer, power drill, carpenter's kit, and so on and so forth. This may be more problematic. For this image, original ImageNet has label and only, but real and really big. For this case, this is somehow ambiguous case, like old original ImageNet has quill and real class feather bore, and this original water jug, real water bottle. And maybe this is more interesting. Original ImageNet for this original label is chain, while corrected one necklace. This can be more somehow problematic. Since ImageNet classes were systematically selected, they may contain some, how to say, hard to distinguish classes. Like for this image, ImageNet original class is sunglass. And for this original ImageNet class is sunglasses. Wow, this may happen. So in corrected one, both may have sunglass and sunglasses. And for these images, original one, laptop, notebook, laptop. And corrected one, notebook, laptop, computer keyboard, notebook, laptop, computer keyboard, and notebook, laptop. So it's more reasonable ground truth were given. And given that in some cases, some image may have multiple classes. And if we regard that each category may be correct by equal chance, then we can generate some classific predicted possible predicted result based on corrected ground truth. So if we do that, we can generate oracle model, and so this corresponds to class, and this corresponds to class level accuracy. And if we do that, of course, some image may have multiple possible classes, and if we randomly choose one of these, they may contain some error. That is why performance might not be perfect. And if we do that, performance can be like this. Means if the chance would be equal, this can be upper bound of the performance. So some earlier method, so the other lines corresponds to the actual performance of the existing image classifiers. So former earlier method can be like this, but more recent one surpassed this oracle performance. This may not be possible, but this means so they will infer how ImageNet ground truth could be, unlike how ImageNet ground truth is biased. It's very well overfit to ImageNet ground truth. So this, well, may not be the right direction, I would say. And if we plot the ImageNet accuracy, this is based on ImageNet original label, and this is accuracy based on collected ground truth, then there can be some interesting finding. So for former method, the performance is like this, but in more recent method, the slope is rather like this. And you can see actually this is the performance of ImageNet ground truth level. As we visited, this may have some error. That is why if we evaluate the performance using corrected ground truth, this is like 90%. And some recent method actually surpasses the ImageNet performance. So this is good thing. So if we use more correct ground truth level, then we can observe uh, more proper improvement in terms of image classification. Okay, I'd like to visit some bias issue. So this is very interesting topic. One paper proposed interesting game, which is called Name That Dataset. And this is that game. You can see a couple of images and grouped into a couple of groups. And the task is to classify each group into a dataset like Caltech 101, Pascal, a Coil, Caltech 256, ImageNet, and so forth. Obviously, normal people cannot solve this problem, right? Maybe we are familiar with somehow this, but not for the others. Maybe computer science postgraduate student working in image classification can solve this, but normal people cannot do this. But if we feed this data as a training data to image classifier, the image classifier can well perform this game. What does this mean? This means that dataset itself is quite biased and it's rather easy to differentiate each other. And it's also mentioned that the ImageNet is less biased, means large-scale benchmark dataset may be less biased. It's a good point. The other more shocking issue, this is about pedestrian detection task, and there is a benchmark data for pedestrian detection, and this shows the performance. Those are state-of-the-art method, and this corresponds to performance. A miss rate, lower the better. So those are top performers. Two different colors corresponds to adult performance and child performance. And you can see for some top performers, error rate for child pedestrian is significantly higher. Means so if we use this pedestrian detection to autonomous driving, that autonomous driving car may misdetect child rather than adult. This is very shocking. So actually, this is due to the skewness in dataset, and dataset contains only 7% child pedestrian. This causes this situation. So this kind of bias is very problematic. Other issue. So ImageNet is known to be very good dataset, benchmark data, and classifier trained with ImageNet surpassed human performance, which means very accurate. However, once we give these kind of image to image classifiers trained with ImageNet, the output is something strange like this. I believe this is former US President Barack Obama playing football, and this is classified into basketball. And this China President Xi Jinping is classified into ping pong ball. Very shocking. And it is revealed that black person tend to be classified into basketball. This is quite bad. And even though the classifier can be very highly accurate, but that may cause some reasonably bad result, like in some cases, racial or gender biases. This may be due to the bias existing dataset. Okay, so let me conclude. So we visited visual recognition, and breakthrough has been achieved thanks to large-scale benchmark data. I believe this is true for acoustic signal analysis. And visual recognition tasks has been evolved, more complicated tasks, initially image classification, and finally visual question answering, seeing graph, and so on, were evolved, were studied. And the benchmark data is getting large scale, and task is going to be large scale as well, large number of classes and long tail. While data long tail distribution is further soaked. Based on that technical progress and design of benchmark are twin. So good benchmark will properly advance the technology. So this is true. While we found that couple of issues in task and benchmark data. When task is properly designed, we need to check whether task is properly designed. We need to check whether sample prior may work or not. This is problematic. And further progress may simply overfit to the dataset. We need to be careful. And bias issues, racial bias, gender bias. We need to be careful about this kind of issue. Okay, that's all. Thank you very much.